Unfortunately, the video device came unplugged or stopped functioning for a minute, and we were right about here, indicating that when we do the gradient, we're applying the del operator to a scalar function, and that's going to give us the gradient, which is a vector function, in a manner where the del f is much like a scalar multiplication of a vector by a scalar. The divergence of f is going to equal the del operator dotted with the vector function. We can't multiply an operator by a function. We don't have a general way of multiplying two vectors. And if we treat this del operator as a vector, we can't just multiply del by a vector function as we could by a scalar function. So we're going to use the dot product. Now that's fairly easily written out. Del dot f being the partial with respect to x I plus the partial with respect to y j plus the partial with respect to z k, dotted with our f of x y z function, which can be represented mi plus nj plus pk. When we do this dot product, we're going to do the I by the I, which means we're going to apply the partial with respect to x times m, giving us partial of m with respect to x. Then the partial with respect to y by the n, putting the j components together, giving us partial of n with respect to y, and similarly with the k components, giving us partial of p with respect to z. And we could also write that as mx plus ny plus pz. Now, as an example, we calculate the divergence of the simplest of the functions we've looked at, the f function, xi plus yj plus zk. Del dot f is then the del operator dotted with our function, giving us partial with respect to x of x, partial with respect to y of y, partial with respect to z of z. Now, partial with respect to x of x is 1, partial of y with respect to y is 1, partial of z with respect to z is 1, so we get 3. The divergence of this function is identically equal to 3. It's not difficult to calculate the divergence of the other functions that we considered, where we divide this by the square root of x squared plus y squared plus z squared, or by x squared plus y squared plus z squared. The derivatives are a little more involved, but they're not difficult. Straightforward application of quotient rule in each case. Now let's consider the curl. Curl is del cross f. Now if we have a general function f of x, y, z, then make sure we're still on the paper here. Okay, so del cross f for our general function f equals mi plus nj plus zk. We don't have any zero components to f, so it's more efficient to write this down using the determinant notation than to use the distributive law. We have partial with respect to x, partial with respect to y, partial with respect to z, and we have m, n, and p. Expanding this determinant in minors, we have then the I vector multiplied by the determinant partial with respect to x, partial with respect to y, eliminating the row and column of the I, partial with respect to z and p, plus j, and that's minus j. Okay, so it's minus j times the minor we get if we eliminate the j row and column, and that'll be partial with respect to x, partial with respect to z, m, p, plus k times the determinant we get when we eliminate row and column of k, and that's going to be partial with respect to x, partial with respect to y, mn. Expanding these determinants now. The partial with respect to y applied to p minus partial of z with respect to n. Now that's pretty clearly partial with respect to y applied to p is, of course, py, and then that's minus nz, and that's multiplied by I. Then we have minus j times the quantity. Partial x with respect to p is p sub x, and this gives us minus m sub z, and then it's going to be plus nx minus my times our k vector. Distributing the minus through here, we have py minus nz times I plus mz minus px times j plus nx minus my times k. For the example function, xi plus yj plus zk, the curl of f is then what? It's we can write it out this way, py minus nzi plus mz minus px j plus nx minus my k. Now our p, q, n, m, n, and p functions are respectively x, y, and z. So what we get is py, which is p is z, so that's the function z, derivative with respect to y. N is our x function, so that's x with respect to z times I, plus m is our x function. No, our n function is m and p is y, not x. In any case, our m function is x, and that's z, and our p function is the z, that's with respect to x, times j, just following the notation here, plus our n function, which is y, with derivative with respect to x, minus our m function, which is x, with respect to y, times k. Now in general, we probably wouldn't follow this formula because it's hard to remember which one's positive, which one's negative, and which one with respect to which variable you're taking the derivative of each. But we could have written it this way with x, y, and z here. I'm sorry, with x, y, and z here for m, n, and p. And we would have obtained the same result. The derivative of z with respect to y is 0. There's no y dependence. There's no z dependence here. There's no z dependence in x. There's no x component dependence in z, and we can easily see that all of these are 0. So that the result is just the 0 vector, indicating that the curl of this field is 0. Now recall that that field diverged from the origin. If you go in a circle around the origin or any path around the origin, you're not going to get, you're not going to get any curl in the sense in which we've discussed it previously. That is, if you do a line integral of this vector field around any path certainly any circle around the origin. If you go in a circle around the origin, the field's always perpendicular to the circle, so there's no component in the direction of motion around the circle. And it'll turn out, we'll prove later, that there'd be no component, if you integrate this function on any closed path around the origin, any simple path, the result is going to be 0. The curl of this function is simply 0. It doesn't circulate around the origin. And furthermore, as we'll see, its net circulation around any closed path is always going to be 0 because the curl at every point is simply 0.